Hello everyone, welcome back to this video. In this video, I'm going to be talking about object classification, image classification, basically using the CIFAR-10 dataset, which is a very popular dataset. Most of the deep learning frameworks that we usually use, like TensorFlow, Pytorch, all of these have uh, built-in functions to extract these data sets because these are very popularly used. We are going to be using PyTorch in this case. So let's begin. Let me just open my collab book. By the way, I'm going to be sharing this collab notebook down in the description so that you can access it anytime you want to. It should be in here. Let me just change the name of this, and let's say now you can go through these instructions that are very easy to understand. You can give these instructions a read so that you can have a clarity about how exactly we are going to implement this. So we'll be using Torch Vision because this is a computer vision application, and for that we have PyTorch Torch Vision to play around. Then we are using some functions in this case. I would suggest you to go through each one of these functions because PyTorch documentation is really amazing. So even a layman can understand it really well. So I'm just copying it, pasting it in here, and you can simply open the PyTorch website here. This is really useful. You should be used to this, reading documentations of different functions. This really helps in developing great understanding of how this implementation works. You can actually see how many parameters are there. So do give this a read. Okay, I cannot take you through every single page of the documentation. It would take a lot of time. Moving on, you can see the CIFAR-10 dataset is basically a dataset of 10 different images. You can actually see these are the classes. I mean, these are classes of it. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So these are 10 classes of having 32 by 32 pixel size, 3 channels. So we have VGR or RGB, whatever you call it. So we have 3 channels, 32 by 32 pixel image, and you can actually see firstly we are going to be load and normalizing the CIFAR-10 training test dataset using torch vision. Then we will be defining a convolutional neural network. Then we will define a loss function. Then we are going to train the network on the training data. Then we are going to test the network on the testing data, and we will then find our accuracy and everything. So before we begin further, I'll just change the runtime to GPU, and let us see if we could run this. So the first thing that you see in here, we are importing NumPy library, matplotlib, because we are going to be visualizing NumPy because we'll be dealing with the array concept of image. So we are not going to be going to any visualize or make any changes to the image itself. So we are going to be converting it into a two-dimensional array. Of course, every image is a two-dimensional array, so we are going to be visualizing only the array. Okay, so we are not going to have uh, you know uh, simple visualization like the image show functions or plt.im show. We are not going to use those functions as far as the normalization and data augmentation is concerned. Moving on, you can actually see these are PIL images. The output of torch vision datasets are PIL image of ranging between 0 comma 1. We transform the tensors of normalized range minus 1 comma 1. So you need to go through all of these these concepts or these lines so that you can have a greater understanding of things. PIL is basically a Python image library, so it's going to be a PIL format. Sometimes we also refer it to pillow image. So moving on, you can actually see we are going to be using this compose function. Is basically used to make all those data augmentations within one function. So we are going to be composing all of those. So in here you can see we are in transforms we are basically converting it into tensor because tensors help us use our CNN frameworks, and all these functionalities that we are going to be doing in the coming part. All of these are will be done using tensors only. So we are then going to normalize our images. This is basically the mean and standard deviation values. Okay, so if I were to show you CIFAR-10 normalize, just the normalize mean and standard deviation. I suggest you guys to go through this Stack Overflow, different websites. Okay, so this will really help you develop great understanding of things. You can see the zero point 0.5 values are just approximates for CIFAR-10 mean and standard deviation values over three channels. You can actually calculate them on your own. Okay, so you can actually see these functionalities that you see here. Using these, you can actually find the accurate parameters of your case. But this is a very popular and a generalized way of doing so. Moving on, you can actually see torchvision.datasets.cfar10. But if you are like working on a custom dataset, then you will have to use a different approach. Because CIFAR is a very popular dataset, you would be having this option in torchvision.datasets itself. So if I were to show you torchvision.datasets, and see this documentation is really important, right? And here you can see CIFAR-10, CIFAR-100, syllabi. These are all the data, popular data sets that are there. MNIST, you must be knowing MNIST is a very popular data set. Then we have Fashion MNIST, we have FLAS, we have, I think we should be having IRIS also. You can see this one, that alphabet and the numericals, 1 to 9 numerical data set. This is MNIST, is a very popular data set. Moving on, you have like a lot of data sets. You can use these. You have the Stanford cars. You can just use these data sets. So all of them are going to be having the same implementation. Okay, so Pytorch documentation is one of the best and easy to comprehend, because the terminologies that they are used are not really complex. So you can see we are going to be doing the same. These are some parameters in this case. We are distributing it into the val set and val loader, train set and train loader. So this is going to be for training, and this is going to be for validation. These are the classes that we have. I have to remove the comments in here. Okay, so I'll just load this and see. You can see we are going to be downloading this. I'm not going to execute each one of these cells because it is going to take a lot of time, but just use this Google Colab and try making your own changes into it. But just by going to this runtime and choosing run all option, you would be able to uh, you know build this model. Okay, you'd be able to run this model on any image that you want to. So here we are going to unnormalize the image that you have. So before you try understanding this, I suggest you to go and find more about mean and standard deviation, particularly the standard deviation thing. How do you exactly find it? How does the normalize function works for Pytorch? This is really important. So unless you go through that normalization function and you get how exactly the formulation works, you would not really be able to understand these things, because this is simply the unnormalization that we are going to be doing, def image show function. So I'm not really going to run all of these, although I'll run this because it is not going to take a lot of time, but I'm not going to run. Okay, so this, I'm really sorry. I'll just have to. That should run. No, I think this should be okay. Yeah. So we have a tensor here. We have some randomly extracted classes. We are now defining the convolutional network. You can see in here. These are basically two functions that we are going to have. The first one was be the init function, where we are going to initialize the layers that we have. Then we have the forward function. Here we are going to implement what we have defined in the initializing layer. You can actually see at the very beginning, we have three input channels, as I told you earlier. Like we have 32 by 32 and three images. Then we are applying 16 filters in this case. Then the kernel size is tuned to 3 to avoid overfitting. Stride is one. I have added all these comments just to have you guys a better understanding of how things work. You should not really get confused after giving all these comments a read. Okay, like this is really straightforward and very simple. I'm not using any kind of complex terminologies in this case. This is very straightforward. In the next video, I'm definitely going to explain you how exactly this max pooling, kernel, filters, how all these things work. I'll definitely make a video on this because I often find it a little confusing to see Even myself, I usually forget what exactly these things do. So I also sometimes need a revision class to remember all these functionalities. So I'm going to be making a very straightforward and a very simple video for filters, kernels, and max pooling, whatever we do in here. The ReLU activation function is what we are going to be using here. I'm going to explain everything in my next video, like why do you use ReLU and how exactly it works, the mathematical concept behind ReLU. Else I'm going to do one thing. I'll just if you want me to, then I can add a few links in the description where you can find the best explanation of ReLU, because I have gone through a lot of videos on YouTube where there are like hundreds of videos available explaining all these terminologies, but I found only two or three of them which are really good. So moving on, you have the classification. We are using the cross entropy function and we are using the stochastic gradient descent. In here you can see the optimizer that we are using is not Adam optimizer. You have to keep that in mind because we usually use an Adam optimizer only, but in this case we are going to be using stochastic gradient descent. But we are going to add a momentum of zero point 0.9 to reach the local minima as soon as possible. Then we are training the network. I'm running it only towards 15 epochs. If you want to increase it, you can increase it to 20, 25, 30, whatever you want to. Moving on, you can actually see we have reached an accuracy, validation accuracy of 69.44. Okay, that's a pretty good accuracy because usually you get only 60% accuracy. But if you tune in some more parameters, in this case run more epochs and tune in a lot of parameters, then I'm pretty sure you would get much more accuracy. You can even reach up to like 85, 90, 95 accuracy. You can actually see how the validation losses decreasing with the training loss, but here there is some problem, I think so, but training in parameters will definitely help. Even in this accuracy parameter, we are having the same uh, difference in the the magnitude of the accuracy. Then this is going to save our model, and here we are going to visualize the same thing, so you're not going to worry about that. We then have we are then calling our net function, which we have defined here. You can actually see the class net function. This is basically a class, not a function. I'm really sorry. Then we are going to find the accuracy for each classes. There are 10 classes. You can actually see how accuracy varies for every. So for validation image, the total accuracy that you have is 71%, and then we have 92, 69, 78, 69, 64, 46, whatever it is. And we are going to do one thing. However, okay, so here you see we have picked four different pictures from the training data set. You can actually see iterating it over, and okay, sorry, we are having it from the validation loader, and we are actually printing the class names. Okay, so this is exactly what the class names is. So we have randomly picked a dog, cat, frog, plane. These are four images that we have picked from the validation data, and then we are going to run our prediction model on here, and you can see we have predicted dog, cat, cat, plane. So this is dog, cat. The first two are correct. Third one is frog. Okay, we have got it wrong. It was a frog basically, but we got it as cat. Okay, never mind. Then we have plane, and we were able to predict it the same. So yeah, it worked really well because I believe it is it worked really well, man. But if I trade it over, I might get better results, but even I could get even worse results as well. But there are like two important steps through which you can make your model really accurate. Is firstly you can do the data augmentation thing, on the top of which you can see. Okay, so here you can see we are not doing any kind of data augmentation. If I show you data augmentation Pytorch, you can see. So this, and here you can perform a lot of functions. Okay, you can have center crop. You can see transforms on PI image with torch sensors. You can, once you have converted into tensor, you can find, you can implement all these data augmentation functionalities if you want to. You just need to go through each one of these to find which one do you need to use, because there are a lot of many. So you can see you can implement all these data augmentation tool. This really helps. Believe me, this really helps in improving accuracy of the model. So thank you so much for watching this video. If you have any doubts, then do let me know in the comment section down there. And in the next video, as I told you earlier, I'm going to be making a video on the terminologies that we usually use in machine learning and deep learning models while building. And also we will be going through CNN network through each one of those layers, and I'll explain you how things would work. And we will also try tuning in different parameters, and meanwhile I'll also explain how each parameter affects the accuracy of the model ultimately. So that is it for this. Thank you so much, and you can access to this notebook through my GitHub profile. I'll be posting that link down in my description. Thank you.